All right, we're going to continue with what we did in the last lecture before the review lecture for the exam. So going back basically 2 weeks, we were talking about center of mass and moment of inertia. And we didn't get to do the actual, I'm going to skip over that. We didn't get to do our actual calculation for center of mass or moment of inertia. We only talked about the calculation of, I think it was the acceleration of gravity in the Earth. Wasn't that all we actually did? So that means that on the next test, the ideas of calculating center mass, well, center mass would have been the last test. Moment of inertia would be on the next test anyway. So they'll both be options for the next test. So the equations that we have in general physics for center of mass and moment of inertia, I've already gone through this slide, the definition that center mass is the average position of the mass. So you take weighting factor of mass times the position divided by the total mass. Or moment of inertia is the mass times distance squared, add all those up. It's not divided by anything this time, it's just mass times distance squared. But remember that distance needs to be the distance perpendicular to the axis of rotation. So the location of the axis and the orientation of the axis both will make a difference to the moment of inertia. Now, if we take these from algebraic equations into calculus equations, it's real simple. What is the capital, what is sigma? What is that in the alphabet? It's a capital S. And in calculus, we replace it, oops, I'm in the wrong pen mode. In calculus, we replace that with what looks like a capital S, an integral sign. Except for, of course, S is usually about farther that way. Just as a point of reference, the symbol that we use is the symbol that French dude, this name I can never remember, something like Leibniz or something like that. That's the symbols that he came up with because apparently Newton was not gifted at explaining things. And so his nomenclature and his explanations of things are generally considered hard. I've never read Principia Mathematica because I don't have that kind of attention span. But I understand that it's really hard to understand because he doesn't explain things very clearly. And then we have XDM. How do we know it's dm? Because that m was a piece of mass at a position x. It wasn't a piece of position x, right? So it's the thing that was the small piece. The x could be really large. I could have mass, calculate the moment of inertia about the corner of the room. And so I'd have the distance from here to Aaron is x, and the mass would be Aaron's mass. And then I go from here to Caitlin, the mass is Caitlin's. If we're going to do continuous distributions, the masses are going to become little tiny things, but the distances aren't going to become tiny. So there I put the perpendicular to make sure it's really clear that we're not taking the radius, we're taking the perpendicular radius. It's going to be important because when we look at cylindrical coordinates or spherical coordinates for our integrals, r is one of the variables. And so if you just leave it as r and don't put r perpendicular, you tend to think, that's just the r that's the variable. But it's not the r that's the variable. So that's why I put the r perpendicular very distinctly, and it hopefully will make more sense when we actually get to it. I've discovered how to make pages that are blank show up. So here are those equations written out where dm is the mass in some tiny region dv. By its very nature, this is a three-dimensional problem because we're dealing in 3 dimensions of space. And so dv can be a difficulty. And for last time we talked about this, I said many times you can, if you have a symmetry such that there's no change in whatever your area is, whether it's spherical or cylindrical, then you can say dv is the area times dx and just have an equation for area, whatever it is. So for instance, if you have a spherically symmetric distribution of mass, then you can say, well, I'm going to make spherical shells of area. The surface area of a sphere is 4 pi r squared. So of area 4 pi r squared, and then my dx is just the dr. And so I would just have 4 pi r squared dr would be my dv if I have a spherically symmetric mass distribution. Okay, so let's get to our first problem. I wanted to do these before, we didn't have time. So 2 problems here. Find the center of mass and moment of inertia of a uniform rod of length L. Now I say uniform rod, I mean that it is of negligible thickness in any dimension. Its only real parameter we need to worry about is the length. So let's start with the simplest thing. I need to have a density, right? What's the definition of density? Mass over volume. Well, if it's really just a one-dimensional problem, if the thickness is negligible, it's just a length, then we actually go to a different symbol. This lambda is equal to a lineal density. That is, it's the mass per unit length. So you see there, mass over length is that lambda, the lineal density. And so it's going to be just a one-dimensional problem. Instead of rho dv, I'll have lambda dx. So looking at my center mass equation, x center mass was equal to the integral of x dm over integral of dm. Well, using this definition of the lineal density, what is my dm going to equal? How much mass do I have in a very small length section dx? If I have lambda is the mass per unit length, if I have some little piece of length dx, how much mass is in that region dx? It is actually shown. Yeah. The dm, the mass in some little region dx, is going to be the mass per length lambda times that little piece of length dx. And so I need to decide where I'm going to find the center of mass, what reference point. So I will choose my reference point to be right here. So that's going to be 0, 0. And in the x direction, x center mass is going to be equal to, why do I need to have that reference point? Because I need to know my limits. What is the minimum x in this integral? 0. So my lower limit is 0. What's the maximum? L. 0 to L. And then I'm just going to have my x times my dm, which is lambda dx, over integral from 0 to L lambda dx. Right, because the bottom was just integral over dm. Now the integral over dm had better give me my mass. So I do the bottom integral as kind of a sanity check. So if we do these integrals, I can factor out the lambdas on top and bottom. Now I've had some people who have tried to combine those into one integral. That's not the way integrals work. You can't combine those integrals. They're just going to be 2 distinct integrals. So the top one, it's a simple integral. What's your result? I'm changing color to make sure we're clear that these are separate integrals. And the bottom one? Now I'm going to put the limits in. Of course, the lower limits are just going to be zeros, right? So the lower limits are trivial. So that's lambda L on the bottom, and on the top, lambda L squared over 2. Now my sanity check. Lambda L. If lambda is m over L, then what's lambda L going to have to equal? M. Good. Because that's what the bottom was supposed to be, the total mass. I didn't, strictly speaking, have to do the bottom integral because I knew it had to be m. But I did it just to make sure that I have the dm right, that it comes out the way it's supposed to. And of course, in this case, another thing that's nice is the fact that I did this integral, I can cancel out, which you were probably waiting for me to cancel a long time ago, the lambdas, and I can cancel out one of the L's, and I'm left with L over 2. And that is absolutely no surprise to any reasonable person, right? Any reasonable person would have said, yeah, the average position of the mass, if it's uniformly distributed, should be at the center. But we just did the math to show that. Now, the problem could be much more difficult. You could have a mass distribution that changes with length. For instance, if we had done something like this for the Earth, the mass distribution changes, right? The density is lower as you move away from the center. And so it becomes a much more complicated problem in that case. And of course, where do we do those complicated problems? Homework and tests. Ain't nobody got time to do you know what the problem is? I have to sit here and think about what's a reasonable equation for the density of a function. You know, that's what makes it hard. I mean, I could give you just a polynomial. You do the integral of the polynomial and you get your answer. But that doesn't make a lot of sense. And so I didn't come up with a sample problem for here's a rod with changing mass density. Okay, let's go to our next thing, the moment of inertia. Now, when you do the moment of inertia, you need to decide your axis of rotation. So there are two likely, well, really, I could say 3 likely axes I might consider. One would be the end, one would be the center going around, and then one would be the center coming down the rod. Now, let's do one of them just in our heads without any calculation. Which one can we do just in our heads without any calculation? Yeah, if we're going down the center of the rod and I said it has no thickness to worry about, then what is your R perpendicular? It's going to be 0 for everything. And so I would get 0 for that. And you might think, well, that's pretty contrived and silly. No, it really isn't. You guys know about molecules. And what are our common molecules? Well, what's the air made out of? Nitrogen, 79%. Oxygen, 21% roughly. Anything else is negligible besides those two. Well, both of those are diatomic molecules. If you draw the figure for those diatomic molecules, you draw a figure that looks like this. And one of the things that we worry about in physics is about the energy that each molecule has. Now, we've learned so far energy can come in different types. What types of energy can I have for this diatomic molecule?
Potential energy.
What kind of potential energy would it have? By the way, we don't consider gravitational potential energy in this calculation. Molecular is not the name for it. You're obviously thinking in the right direction. It's what?
Nuclear?
Not nuclear. Okay, it is electromagnetic. But we model these. Carrie will come and borrow a spring because we can treat for small oscillations as if this molecule is held together by a spring. And that spring has a certain rest length. And at low temperatures, you don't have enough energy for it to vibrate. And so it's just sitting there at its rest length. There's no potential energy there. But if you get to high enough temperature, it can start vibrating. And so we call it vibrational energy because it's actually two pieces. You have kinetic energy associated with it moving back and forth, and you have the spring potential energy. We just treat that electromagnetic force as if it's a spring with spring constant K. You can go ahead and calculate. And so you have 1/2 kx squared plus 1/2 mv squared for the speed of vibrations. And it goes back and forth between the kinetic part and the potential part, but it stays constant. And so the first type of energy that we actually talk about here is vibrational, which is not the goal today at all. I'm just going off on my own here, but it's one of them that's there. Second type, what other type of energy could it have? There are two more, by the way.
Kinetic.
Okay, kinetic. Now this vibrational had a component of kinetic, and the other two are both kinetic. And so we have to break those two kinetics down into the types of kinetics. This is what we've recently talked about. What types of kinetic energy can it have? Rotational and translational. So the translational kinetic energy is 1/2 mass of the molecule times the speed of the center of mass squared. The rotational is 1/2 I times rotational velocity squared. And I'm going to put, well, I'm not going to put it here. I will mention it. The vibrational is a little more complicated, so I'm not going to write its equation out. A final thing on this, right? I'm going to some things that show why that talking about the moment of inertia was important and not trivial. If we talk about the rotational portion of the kinetic energy, well, first let's talk about the translational. We break the translational up, and this sounds wrong, but it's right. We break it up into three parts. It's kinetic energy associated with momentum in the x direction, momentum in the y direction, and momentum in the z direction. So we talk about kinetic energy as having three parts, one for momentum x, one for momentum y, one for momentum z. And so we actually write this with three pieces: px squared over 2m, py squared over 2m, and pz squared over 2m. For the rotation, we have the same type of thing. We can have rotation about different axes. So if I have something that's like my pen, I got to make up three axes, right? And so the three that we choose are one that goes like this, one that goes like this, and then what direction is perpendicular to both of those? The one we just calculated. But what was the moment of inertia for that axis? 0. And so there's no energy that you can put into that rotation. There's only energy for this rotation and for this rotation, but not for the third. So there are only two pieces here. So we're going to have 1/2 Ix x omega x squared and 1/2 Iyy omega y squared. But there's no 1/2 Izz omega z squared because Izz is 0. So that's why that wasn't a trivial calculation. When we get to the equipartition theorem, which will be like in another 2 weeks maybe, it's coming up pretty soon. No, it's 2 weeks? No, it's second semester, my bad. We'll learn that nature tries to put the same amount of energy in each possible way it can have energy. And so when we talk about that rotational energy, there are only two ways you can put it in. So at low temperatures, you can't have rotation or vibration. All you can have is the molecules moving, which sounds really bizarre. Like, why can't it go like this at low temperature? but quantum physics says it can't. And so at low temperature, the molecules are just moving around, not vibrating or rotating. And so you have amount of 1/2 K, a constant, T in each of those three dimensions. So the total energy of the molecule is 3/2 kT. When you get the temperature up higher, you can start to put energy in, and I think it's rotation first, but it could be vibration first. But you can start putting energy in one of those two. Both of them actually have two, what we call degrees of freedom, two ways you can have energy. The two ways for vibration were the potential energy part and the kinetic energy part of the vibration motion. The two ways for the rotation were the x and y directions. And so it goes from 3/2 kT to at middle temperatures 5/2 kT for the total energy. So the relationship between temperature and total energy changes when you get up into higher temperatures because you have more ways you can store the energy. And if you get up to really high temperatures, you can store energy in all of these. And so it goes up 2 more, and so it goes to 7/2 kT. So now that's all of that stuff is nothing you're going to be held accountable for until second semester. But I wanted to point out that there's actually reason to consider that there's no moment of inertia about this rotation. It is a real life problem. I forgot that this class did start at 11. I was like, I'm out of time? Okay, so let's calculate the moment of inertia about the center of this, going like that. So if we do that, I'm going to have still linear distribution. So I'm going to do it about this axis, and I'm going to call this the x-axis. Now it's called IXX because remember, moment of inertia, I said it's really a tensor. You have 6 unique values for it. But most of the time, especially general physics problem, if they're both the same, we'll just write one of the index and call it IX. And for all our purposes, that's all we're going to do is count IX. IX, potentially IY, but in this case it'd be the same. So IX is equal to the integral of r perpendicular. Well, if my x is going from here out, then how does r perpendicular relate to x? What's the angle between this? Oh man, I can't use x 2 different places. Somebody should give me a brain check. So this is going to have to be y. So how does r perpendicular relate to x? What's the angle between x and my y-axis there? 9 degrees, which we often call perpendicular. So that x direction is perpendicular to the axis of rotation. So r perpendicular is just equal to x. And so I have r perpendicular squared, so x squared. And then I have to have my dm. Well, we had right there, dm is lambda dx. And I do my calculation. Integral of, oh, what are my limits? Got to do that first. If x is measured from the center, I'm going from minus L over 2 to plus L over 2. So getting those limits is an important piece of the problem. So now let's do the calculation, and we will have integral of x squared dx is x cubed over 3. Put in those limits, and what do I get?
Over 2 cubed minus over
Plus
3
L over 2 cubed.
plus
Okay, there I put it in explicitly. Notice I have minus a negative L over 2 cubed. Minus L over 2 cubed is negative L cubed over 8. Minus a negative L cubed over 8 is plus L cubed over 8. So that's L cubed over 8 plus L cubed over 8. Which of course is L cubed over 4. And then I had the 3 out front. So my answer comes out to be lambda L cubed over 12. That's not the way it showed up in the table. Why is it not the way it showed up in the table? Because the table puts mass in. I have lambda, so how do I convert from having lambda to having mass?
Substitute M over L.
Yeah, lambda is equal to M over L. And so that means I'll just cancel out one of the L's. And so I have M L squared over 12. So that's the moment of inertia if it's rotating about the center. Well, what if it's not rotating about the center? What if it's rotating about the end? What changes in my entire calculation if I rotate about the end?
Just the limits, right?
Just the limits. Now, I did this calculation, by the way, doing it for a rod. I forgot that I had the diatomic molecule here, which does not have continuous distribution in my picture. So I'm just going to change the picture so that now I have my continuous rod there, not the diatomic molecule. So if I did about end, it's still going to be lambda over 3 times x over 8, but now it's going cubed. But now it's going from 0 to L. Well, now the lower limit's just going to give us 0, and the upper limit will give us L cubed. That wasn't x over 8, now was it? It was just x. I put that 8 in because I wasn't thinking clearly. The 8 came from 2 cubed before. So notice it's 4 times bigger if I did it about the end than if I did it about the center. So you have to pay attention about the axis you're rotating about. Makes a big difference. Any questions about this calculation for moment of inertia?
I'm still trying to visualize what axis you're rotating about.
Okay, yeah, this one here was, here's my rod, and I was rotating about this axis.
Oh.
And so my x here was going from 0 out to the entire length L. Thank you for asking, so I can put that in the picture, and then there's some clarity. Except for I put that in a very poor place, because I put it in the middle of the work up there. Okay, there's a better place for the picture. Any other questions? Yeah.
Is that the same then as the moment around the x-axis? Like if you're rotating it like that, or would you have to?
So these were if I rotate it like this, right? Mm-hmm. So if I rotate it like this, I would get the same numbers because the symmetry is the same. Yeah. And of course, if I rotate it like this, then I get 0. Which makes no sense at all in the recording, so. Okay, let's go to the next case. A thin circular disc. When we use the thin circular disc, we have a cylindrical symmetry now. And so it is most convenient to solve our problems using cylindrical coordinates. So on the right side here, I have depicted what the cylindrical coordinates are. Just to make it simple, roughly a cylinder, much lighter than the example this one here is fine. Here's a cylinder. The cylinder has a symmetry axis that goes up the center. And so the key starting point on cylindrical coordinates is you have a cylindrical axis that comes up through the center, and we call that the z-axis. So the z-axis is the symmetry axis. You have then your radius, which is measured perpendicular to the z-axis. So the radius is in this plane here. And then finally, because it's symmetrical, a rotation is the last coordinate. That's different than what we've done before, because our coordinates before were spatial, that is x, y, and z. They all had dimensions of distance. What's the technical dimension for a rotation?
Radian.
It's what?
Radian.
Radians, which are units of
Angle.
nothing. Right, so there's no unit associated with that. But if I'm going to have dV, d volume, I need to have units for dV of distance cubed. So my dV can't be dr times dz times d theta, theta being the angle for the rotation, because that would have the wrong units. So this picture on the right illustrates how we get the right units. So this picture is showing a piece of mass, well, actually a piece of volume here. Now, is this volume a cube? No, it's not. But we treat it like a cube. Why? Because if it's infinitesimal, then the error between treating it as a cube and treating it accurately is on the order of 1 over infinity cubed, which means that error is really not important to us. And so we treat it like it's a cube. And so to find the volume of the cube, dV, we just have to take the dimensions of the cube. So I drew too many dimensions here. Let me, that was supposed to be erasing. Let me just highlight the dimensions as shown. So here's one dimension. R d theta is the length of an arc for angle d theta. dr is this dimension, and dz is this dimension. So if I'm going to treat it like a cube, I'm just going to take those three, right? A cube, the volume is x times y times z, or base times width times height. And so my base is r d theta, my width is dr, and my height is, I should zoom this in because you can't see this, can you? So there's my width is r d theta, my length dr, my height, come on, Richard, my height dz. And so I just multiply those together to get my d volume. And so multiplying those together gives me d volume equals r dr d theta dz. R dr, the first one, or excuse me, if you want to put it in the order there, I will change it so it's in the order there. Oh, doggone it. Delete, go away. I pressed the wrong button in case you're wondering. It's my fault. So the first one was r d theta. The second one was dr. And the third one was dz. But we usually write this as r dr to get the r's together. D theta and dz. So that's my integrand, or not my integrand, but my dv. Now if I go back to my disk, I'm just going to find the moment of inertia about the z-axis here. So if I find about the z-axis, I would have I, and notice here it has zz, because that's technically how they do it. Iz is equal to the integral, and what's the first thing I have to put in my integral? It's the r perpendicular squared. So I need to find r perpendicular. Well, in terms of my three variables, here you see theta is an angle that's going perpendicular to the z-axis. R is also perpendicular to z-axis. And then z is, of course, parallel to the z-axis, surprisingly enough. Which one of those is, well, how do I get my R perpendicular? The perpendicular distance from the z-axis to where my mass is. Do what? It's just R, because that R is already perpendicular to the z-axis. So in this case, R perpendicular is just equal to R. And so that means I'm going to have R squared. And then for my dm, I have the dv here. dm is equal to density dv. Well, in this case, I'm going to have negligible height. If I have negligible height, we can do this easily by simply saying that means that I don't have a dz to worry about. It's negligible height. So I'm just going to drop the dz off and just say it's two-dimensional, and that I will have, my rho will become sigma is equal to mass over area. And so dm is equal to sigma d area, which is sigma r dr d theta. So that's what I'm putting in for my dm here. I redefined a new variable sigma for the areal mass density. That's what we call it. And so sigma r dr d theta. Well, I do my integral. What are my limits going to be? Two integrals. One, notice r squared times r is r cubed dr. The other one, d theta. Bring the sigma out because it was a constant. What are the limits going to be for r? 0. Radius has a minimum of 0. Out to, and so I'll use a capital R so we're clear. It's the radius, capital R, then will be the radius of the disk. And what about the angle?
0 to 2 pi.
0 to 2 pi, because we have to go all the way around the circle. To get to all of the mass, I have to go from 0 radius out to the full radius, and I have to sweep around the entire circle. And so that would be 0 to 2 pi. Now these were completely separable integrals, so they're two simple integrals. What's the integral of 0 to 2 pi d theta?
D. Just 2 pi, right?
Yeah, that's just 2 pi. You have theta going from 0 to 2 pi, which is equal to 2 pi. Well, what about the integral from 0 to r of r cubed dr?
R, capital R to the 4th over 4.
And so you put those together and you have Iz is equal to r to the 4th over 4 times 2 pi. And I forgot my sigma. There was a sigma out front. Of course, we want to now go from the sigma back to mass. So the relationship between sigma and mass was that sigma is mass over area. Mass over area. What's the area here? What is it the area of? The area of a circle. So the area is pi times radius squared. Sigma is equal to mass over pi times radius squared. So if I put that in, I will have I can cancel my pi's. And I can cancel 2 r's. And I can cancel a2. And so I have 1/2 mass times radius squared. Which you saw right there. Now that wasn't so hard, was it? Nah. So notice that's not the only calculation here. They did IXX and IYY. They're the same thing because of symmetry. How do you do that? What's going to make this more complicated?
Instead of it is spinning, it's like.
Okay. Yeah, my radius is no longer r perpendicular. I'm going to have to figure out what r perpendicular is. So I realize I need to insert a page here. Oops, I just want to put in one. So let me go to the next page that I just made, and I'm going to draw this with a vertical circle. So I'm changing the orientation so I can have a vertical circle. Okay, there's my vertical circle. And then I'm going to have a vertical axis. And so that axis is going to be my x-axis. So it's rotating about this x-axis. And so now, where should I measure my angle from? Where would you like to measure the angle from in this rotated picture? Guys, where would you like theta to be 0? I let you choose. What'd you say, bro?
At the x-axis.
Okay, at the top. So what he's saying is, let's go ahead and measure theta. I was afraid of that. It started misbehaving there. Stop. Come on. Close it. Open it. And come back to working, baby. Please. Yep. So we're going to measure theta like that. Right? Because we just had to choose where we're going to measure it from. Now, if I want to find r perpendicular, what is r perpendicular measured perpendicular from? The x-axis. So if I am at some angle theta, then my r perpendicular is going to be that. And so what would r perpendicular be equal to? R times sine theta, because it's the opposite side. Why R? Why not capital R? Because, of course, we're going throughout the entire disk. So we had to calculate a new value for r perpendicular. And so now I will have Ix is equal to the integral of r sine theta quantity squared times sigma, that's a sigma, sigma r dr d theta. It's still separable. And I still have r cubed dr for the first one. But for the theta, I have sine squared theta d theta. I have to integrate that sine squared theta d theta going from 0 to 2 pi. Well, what is the integral of sine squared theta d theta? From 0 to 2 pi. You know how I do this, folks? How?
Double integral formula?
No. I do this graphically. This is one of those situations where a graph makes life easier than calculus. And I don't know how often that occurs, but this is one where it does. If I graph sine squared theta goes like this. There's one cycle. It's symmetric about the center point. The top, sine squared theta, is going to be 1, right? 1 squared is 1, because it goes from -1 to 1. For sine theta, you square it, it's going from 1 to 0. And if it's symmetric, going from 0 to 1, then if I calculate the average, if I calculate the area under the curve, it's going to be the average height times the width, right? The average height is 1/2, and the width here is just going to be one cycle. And so that integral actually just gives me a value of, graphically, 1/2. Isn't it nice to be able to use your brain and not, well, use your brain. You would have been using your brain if you would have done, integral of sine squared. I mean, could have done integration by parts, There's a few annoying ways of doing it, but that's the easiest. The other way of doing it is actually, the other easy way is to use the substitution that sine squared theta is equal to 1/2 times, 1 minus cosine, 1/2 of 1 minus cosine of 2 pi, or 2 theta, whatever it is. And then the average of the cosine over an integer number of cycles is 0. And you just have 1/2 again. Okay, and the first part we already saw, we already did this calculation. So we have that. And, actually, it's over. That was 2 cycles for the sine, though. I think this actually came out to be 1 because it was 2 cycles. Each cycle has an area of 1/2. Okay, my easy method failed me. I forgot it's 2 cycles. I'm pretty sure that comes out to be 1. So now if I put that together, I will have sigma it turns out I did that wrong. I did it wrong. I did it wrong because the limits are 0 to 2 pi. It was 2 pi on this and 1/2 for the vertical. So 1/2 times 2 pi is pi. Is that what you just said? Yeah. At least I got there. This took me a while. There'll be a missing gap in the lecture recording. No, there won't be. But so we have, there we go. And so substituting for sigma is mass over 2 pi, or pi r squared. Then I'm going to have the canceling of pi's, canceling of 2 r's. So it's 1/4 mr squared, which is what it had there. So what did we not get to? The spherical coordinates. We have 2 minutes, so let me just introduce spherical coordinates. Obviously, we don't have time to do the problem. Spherical coordinates we use when we have spherical symmetry. So if I'm doing something like, let's say, a solid sphere, this isn't solid, but if it's a solid sphere, because it has spherical symmetry, we use the spherical coordinates. But with spherical coordinates, you use r as the radius going from the center out to your mass, no matter what angle the mass is at. And then we use 2 angles to get the angle it's at. One that's going around, again, 2 pi, and one that's just going from vertical to vertical. It's only going through pi. Why only pi? Because if I kept going, I'd be covering the second half of the circle. I already covered that by going 2 pi this way. And so your angle theta goes from 0 to 2. Well, actually, in this picture, it's phi. The angle phi is going to go around a complete circle, so from 0 to 2 pi. But the angle theta, the vertical one, only goes from 0 to pi. And notice the angle is shown here is measured from the positive z-axis. In your math textbook, you might have seen this with it measured from the xy plane. You get the same outcomes, but you have slight differences. So you need to pay attention to where you define your variables. So once again, this isn't a change pins. Black isn't going to cut it for me. This isn't a perfect cube, but we treat it like it's a perfect cube. With this side here having a length of r d theta. This side here having a length of, it's shown out there, r sine theta d theta. And this side here, well, I'm going to write there, having a length of dr. And so to get dv, you have to combine all three of these. And combining all three, you get dv is equal to, you had r in r d theta, well, let's just write down. It's r d theta times r sine theta d phi times dr. So you have r two different places, r squared sine theta dr d theta d phi. And so that's your dv term. Then you just go through like you did before. The key is to find r perpendicular. If we're doing a uniform sphere, oh man, I was gonna say I have a minute because it only takes a minute but I have less than a minute. I have minus 1 minute, so I won't do it. But you just have to find the r perpendicular, and the r perpendicular will be, well, it's going to take me a little bit of time to show the geometry. I didn't have it memorized. So let us end the lecture. Actually, it won't take me any time at all. That's theta. The opposite side is the perpendicular, so it's r sine theta is the r perpendicular. And then you just do your integral of r perpendicular squared times rho r squared sine theta dr theta. Okay, have a good lunch. I'll see you back here for lab in a little bit.